Proud to introduce our new speakers. Cael Gniel is a registered professional geoscientist, mineral resource estimation, with over 10 years of international and domestic experience in the mining industry. He has experience across the mining value chain, having worked in exploration, underground, mining, resource geology, and mineral processing. Cael now applies his breadth of experience to blast movement as the product owner of the Augment Technologies. Bryce Gower will be joining us as well. He's the co-founder and CEO of Augment in the past 6 years, and he's extremely passionate about solving a problem that has only been mitigated, on his own words, and I believe, on the last few, on the past years, in open cut mining, which is pretty much ore loss and dilution from blast movement. Very exciting technology, and I'm very pleased to have them in here. Cael, Bryce.
So thank you, everyone. So I'm just here to give a quick layup to Cael. Augment has had a partnership with Datamine for quite a few years now, and so many people in the room may have seen some of our previous presentations, but for those of you who we are new to, I just wanted to introduce the company, what we do, before handing over to Cael, who will walk you through a really good value demonstration of what we do, including a novel mark-out technique at the end. To quickly introduce Augment, what we are here to do is to take AI technology and focus on the mining sector and solve problems that have plagued the industry for decades. We're coming at it from a new perspective of what we could not do before AI technology was where it is today. And we are blindly focused on mining. And actually, we don't even try to help underground mines at the moment. We are explicitly focused on open cut. And we are here because we really believe not only in maximising the resources for everything in this world that is built on our products of our mining operations, but we are really committed to what geologists care about in stewardship of the ore. We can oversimplify it to saying we want to help you get more ore because that's more money, but it's actually about the care of the ore, why we talk to geos and not so much mining engineers or drill and blast people, because making sure this rare event of geology that has occurred is actually utilised and disseminated in a way that humanity can benefit from it is really meaningful to our team and our purpose. So what I want to introduce to you is the Muckpile Block Model. If that's not immediately apparent what it is, you can see we've got two surfaces that we use. One of the pre-blast, which is the video playing now, and we use that pre-blast surface to slice your grade control model. So that slice of the grade control model, you can see, becomes a nice little basis of your grade control platform, and we subcell that to a cubic meter scale. So the surface of the post-blast arena, now you can see, also has a block model that fits perfectly to it, but none of those blocks are new. Every block in that post-blast Muckpile block model has come from your in-situ grade control model. All our solution does is relocate cubic meter blocks in space. So you have a flawless balance of tons and grade in the Muckpile block model to what you had in situ. And because it's based on the surfaces, it's actually a very accurate volume estimation, shaving away 1% errors every place that we can. And as you can see in the last graphic, the Muckpile block model at a cubic meter resolution was too much precision to mine from. So we have reblocked that up into an SMU scale. So it was really interesting, Dave Berry, talking about your Python functions. We would love a ton grade analysis here of not only what you had before the blast, so you can see the plan, but because the Muckpile block model helps you understand dilution, doing a grade tonnage curve and comparing the two curves is a really insightful activity that we do quite often. And the reblocking is a Python function we could look at open sourcing for you, seeing as you're missing that in your library. So with a quick introduction to the Muckpile block model, I'd love to hand over to Cael, our product owner, to walk you through a value application. There you go, Cael.
Excellent. Thanks for the layout, Bryce. That was a good introduction. And yeah, just getting back to the stewardship thing, just coming from a resource estimation background, we spend weeks domaining, doing variography, doing our EDA, and then estimating something. And then oftentimes we find that the same care isn't taken at the business end of the process when we actually mark it out to go mine it. And so that's where the Muckpile block model fits in. And so, as Bryce mentioned, the Muckpile Block Model is the output of our 3D blast movement solution. And we take extensive data from across the world to precisely track the ore location across all three spatial dimensions. But before I go on and we get onto that use case, I just wanted to kind of have a high-level understanding of the process that the user goes through, or the geologist goes through, to create a Muckpile Block Model. So we have input data, as Bryce mentioned, being the pre- and post-blast surveys. We have drill and blast actuals. That's very important that it's actuals. And we also have the grade control model. And once the user has imported all of these external data sources, they're prompted to create a series of strings which help delineate the pre-blast volume and the post-blast volume. So the pre-blast volume is the volume of rock that's allowed to move in our algorithm, and the post-blast volume is the volume with which that pre-blast volume moves into. Accounting for expansion, and we also include air blocks to account for the decreased density in the muck pile. Now, this user-created step of creating strings is really important because what it allows the geologist to do is impart their significant experience, intuition, and ore body knowledge to affect the result. And that's really important for us because we don't want any of our solutions to be a black box. We want to, as our name suggests, we try to augment the user experience, not delete it. So once all the data has been generated that's required for the process, we have a regularization process that happens locally before it's sent to the cloud, and a Muckpile Block Model's returned to the customer. Like Bryce mentioned, every single cubic meter block from the in-situ model is present in the Muckpile Block Model, and in fact, it's actually a carbon copy of the regularized model that was sent to the server, except with a few key elements added to the file, that being the XF, YF, ZF, the final coordinates. So that's what you can see in the bottom right-hand image, is the final coordinates being displayed of the block model. So this kind of represents a bit of a step change in terms of marking out, because no longer are we talking about translating strings that have been created on an in-situ model. We are creating a mark out on the moved model in the post-blast environment. So what this allows miners to do is to better address the 10 to 20% swings in metal call factor that we see when we do a reconciliation study. You often see like a bit of a sawtooth sort of pattern, and there's many. It's probably the topic for another talk, but there are many sort of error bars in a reconciliation study that I'm sure we can all appreciate. But one of them is definitely ore loss and dilution, of course. And so what using the Muckpile Block Model does is it enables our customers to realise an increase of ore yield by up to 5% sustainably, while also minimising the short-term variations in reconciliation. So let's jump into the blast. We've got here a stratiform PGE deposit with approximately a steady dip of 20 degrees or so. Here I've just got the block model. It's the in-situ model that's been filtered to remove the waste. And you can see that there's relatively consistent PGE grades throughout. This particular part of the mine's high grade, and so essentially all the blocks here sit in the high grade material type. And there's a sharp boundary between the ore and waste, of course, for this type of deposit. This is a visual deposit, so you can see it in the pit. And the next step of the process is to import our drill and blast data. And so what we're looking at here is a simple square pattern with echelon blast timing. We have a consistent drill spacing and burden. There's a few more holes on the free face, but what we're actually displaying here is the timing values. And I find this is a really intuitive way of trying to set the expectations in your mind of what the blast movement's going to be like, because we know that blast movement happens at a right angle to our timing, or timing contours rather. And so we've got low timing values on the right, high timing values on the left. So we would expect a blast movement to go from the left to the right-hand side of the screen. Importantly, as I mentioned earlier, with regard to actuals, we do have several designed holes that have collapsed in this blast. So I just wanted to underscore the importance of using actuals, because it will have a demonstrable effect on the Muckpile Block Model at the end. So we anticipated that it would be a move from the left to the right, or a southeasterly movement, and when we examined the pre and post blast surveys, which is the next piece of data that we'll look at, we do indeed see a southeasterly movement of material. And so you can see that in the two cross sections there. We've got approximately 11 metres of heave over the free face, which is a fair bit, and a small power trough near the pit wall there. And so that's three different domains, and we'll also start to think about the fact that the amount of dilution and the amount of mixing would vary between these different blast domains. And certainly at the resolution of 1 metre, the Muckpile Block Model picks that up. So we've just imported all the data, the users created the strings, and the regularization process has happened. It's been sent to the cloud and returned. On a blast of this particular size, that process should take somewhere around 15 to 20 minutes. It does scale with the size of the blast. And now that we've got, in the first case, the Muckpile Block Model returned at the top and a filtered version of that below. So I've removed all the waste again for the bottom image. And with the Muckpile Block Model in place, we can start to think about a markout. And so the grey shape wireframe there is the original markout, or the traditional markout that was used at this particular site. And what it was basically taking the wireframes that were used to generate the grade domain, or the ore domain for that block model, and then translating it up a certain distance based on observations that they'd made in mining over a period of time as a heuristic, effectively. And that would essentially become their high-grade markout. But you can see that we've got some material that's hanging out on top of the markout there. And you'll also note that that material has a topography of its own. It has like a post-blast ore topography, if you will. And it's quite complex. So it starts to appear like it's complex. If only we had some way of measuring it. Well, like I mentioned, it is a visual ore body, so we can send ore spotters into the pit and we can have a look at what the post-blast environment looks like. And so that's what we've got here. We have our red dots being the top of the ore as picked up by the ore spotter. And then I've just wrapped a DTM around that to try and convey some of the complexity that we see in those measurements. Obviously, it's actually fairly coarse sampling. It doesn't have meter resolution sampling on the top of the ore there by the ore spotters, but it gives a good representation of how complex that environment is. And so you can see that the shaded shape, which is that traditional markout for the high-grade ore in this instance, is not conforming to, for this particular blast, to the ore spotting measurements. And in fact, the amount of error, which is about 2.5 meters on the left-hand side of the image, is actually getting worse. So the post-blast, from what you can see here, the post-blast environment is almost too complex to adequately represent with a simple translation. And that's where the problem comes in for a particular, this kind of ore body geometry, is how do you create a markout around that kind of geometry? But before we go there, we've got some ore spotting data. How does that compare to the Muckpile Block Model? And does the Muckpile Block Model represent that same complexity that I was saying is causing so many issues? So here we've got those two data sets overlaid. On the top, on the right-hand side, we've got the blocks are made slightly see-through, but you can see the distribution of the ore spotting data throughout the blast. And then in the series of cross-sections that we've got, we have our data points in red, against our Muckpile Block Model in green. And you can see for the parts where we do have those samples, there is generally a good agreement. You do find a block here or there it is above, and you do find a block here or there is below. But in general, if we take a quantitative approach, which is always the best, we have approximately a 1 meter error on average between our ore spotting data and the nearest ore block as calculated by the Muckpile Block Model. And there is a max error of about 3 meters. But generally, we would consider that to be a good agreement between the two data sets. So now that we've got our Muckpile Block Model, we can evaluate the traditional markout and see how much of that blast, which effectively all sat in the high-grade bin to begin with, how much of it's been recovered in that markout process. And in this instance, using the traditional one, we have approximately 55% of that ore being caught in that markout, which still gives us a very healthy revenue figure that's going to be brought forward immediately, because we all know that high grade makes its way to the mill first. But we are still leaving a lot on the table. But as we've already sort of mentioned, there's a complexity to this system that is really hard to capture with just any sort of simple translation of a wireframe or indeed a string. The ore body geometry is quite difficult to replicate. So what can we do that's different? We decided that we'd try a novel isoshell markout technique. So just to reiterate the problem, creating an explicit wireframe to this level of detail would be exceptionally time consuming and not a real good use of a geologist's time. So the solution that we came up with, as I mentioned, is to run Studio RM's implicit wireframing functionality inside of a custom script that we created, which it would enable the user or the geologist to rapidly iterate the parameters that get input into that wireframing process to evaluate the tons and grade in each of those scenarios. So if you needed to put the most amount of tons through the mill at a given grade, like a cutoff, you could evaluate that scenario. Or if you were tons constrained and you needed to have the highest grade possible given a set amount of tons that you could put through the mill, you could evaluate that scenario. Using the Muckpile Block Model in this way gives you the optionality to essentially evaluate whatever paradigm you're in. And also, it's critical that this process is only really possible because it is in a block model where you can store these values as points and wrap a implicit wireframe around it. So it's very powerful to have it in proper block model format. Now, subsequent manual wireframing and fine-tuning is probably required, but you've eliminated 95% of the legwork in doing this, and it takes what would probably take, I don't know, upwards of an hour to do something explicitly. You've taken that down to a matter of seconds. But how does it perform? So in this instance, I haven't tried to do anything, any of the manual fine-tuning. I've just run the isoshell. I think I ran 15 different iterations and compared them all. And this was the one that I chose that gave the best tons at above the cutoff grade, or a similar cutoff grade to what the traditional one got. Average grade, not cutoff. And so here we're looking at ore body recovery within this isoshell of approximately 81%. And once again, that's bringing forward a whole bunch more revenue because it's going to get processed sooner during this process. And so as I mentioned, you can evaluate different scenarios, but here we've been trying to get the most amount of tons at a given grade. So I'm just going to summarize a few of those points again in case I went over them too quickly. So the Muckpile Block Model accurately represents the complexity of the post-blast environment to a precision that was not possible previously. The traditional markout method that we saw is not able to represent that complexity, and indeed almost any simple translation would not be able to do the job adequately. And any explicit functionality or any explicit wireframing done by a geologist would take a long, long time. So this isoshell method is considered fit for purpose for them with the manual tweaking, as I mentioned, that's required. And also the isoshell conforms quite well to the ore spotting, as you'll note, between the red being the isoshells and the red dots being the ore spotting. So like I said, this operation needed to maximize tons, and that's what we've been able to do. So for this one blast, we would have sent approximately just a bit over 28,000 tons to the mill in that high grade material type, increasing the recovery by 26% in that material type, and therefore increasing revenue by approximately $1.3 million US.
If you were asked what would be the key differentiator, say, between this software and Orica's OrePro 3D?
There are multiple use cases. So one of the ones that we found to be particularly useful with this is quantifying rill. And that's a use case that I'm not sure anyone else can do. So we have our customers that inevitably, blast over the pit wall and lose some ore during that process, but it's been very difficult in the past to quantify that component. We have customers now that maintain their Muckpile Block Models and effectively have a stockpile at the bottom of the pit which they've quantified and can use our product effectively in that instance. And of course, there is the fact that it's interoperable. We can fit into any GMP. Obviously, Datamine is great, but everyone has their preferences, and we can essentially, the Muckpile Block Model is returned as a CSV. So if you can import it into a CSV, then you can use the Muckpile Block Model. We are fully agnostic.
You highlighted at the start that the input data is really important in picking up things like holes that aren't charged. How much does things that happen during blasting, misfires, mischarging, mistie-ins, how does that affect this system if you're not actually measuring and checking that movement's correct?
Yeah, that's a really good question. So some people do drone footage during the time of the blast. And so if you've noticed that there have been misfires and stuff, you could potentially go back and try and edit that in the input data before you import it. But really, it's a matter of... I guess the best way to do it is to understand what the impact of it's going to be. And what we find is if we run it in multiple instances and get a distribution of results, we actually don't find that there's a huge difference, but we're chasing nines here, right? So we're trying to be as accurate as we can. So we always say do the best to get the best data you can. But ultimately, we find that the impact is not impactful at the SMU scale, if that makes sense, because we don't mine individual 1 meter blocks, we mine SMUs. So when Bryce showed the SMU model, most of the differences can be accommodated or can be removed or negated to a certain point at that SMU scale, and even less so at the mark-out scale.
Well, a bit of a strange question, I guess. When you were saying at the start about obviously using the block model, then going to a bigger scale model, for the post-blast, if they're different sizes, how does the model conversion work out? What should be the same block as ore? If you're is it proportional? Do they look at the small units and go, that should be ore because it has to apparently equal the same that comes out?
Yeah, that's right. So all of the reblocking's is handled in Datamine. So it's just using standard reblock. And we basically just do a tonnage weighted a reblock, and so it can be a little bit confusing for some people that are unfamiliar with reporting the tons and grade using something like FillVol, but it's all conserved once you do the reporting in the right way.
Look, I might have missed something, but is this incorporating some sort of blast movement monitoring if it needed to?
If it needed to, yes, but it does not need any other form of blast monitoring. Once we have the data sets that I spoke about, we combine physics simulation with AI to produce the blast movement. And that's trained on multiple different data sets. or hundreds, in fact, thousands probably by now. And it's that wealth of information that we're drawing upon each time that we do it, so that we can create a generalized model that will produce the right results regardless of your input data. We obviously welcome people to check it against their favorite blast monitoring system, whether that be bamboo in a hole, which we've experienced, or polypipe, or BMMs, or whatever you want to use. But strictly speaking, no, we don't need any of that. It's a software-only solution.